right, so rational functions. A function f of x is rational if f of x equals n of x over d of x, where d of x cannot be equal to 0, and our n of x and d of x are both polynomial functions. The domain of a rational function is a set of all real numbers x such that our denominator is not equal to 0. And we know that, that's nothing new for us. So let's start with something we know. Let's state the domain of our rational function in interval notation. The domain of any function is all real numbers unless we have a variable in the denominator or under an even index radical, and this is the situation where we have a variable in the denominator. So we need to set our denominator equal to 0, solve, and exclude. This factors nicely into x minus 4 and x plus 1. We get that x cannot be equal to 4 or negative 1. We don't want negative 1 or 4, but we want everything else for our domain. What is that domain going to be in interval notation?
Is it negative infinity to negative 1, and then negative 1 to 4, and then 4 to infinity?
Perfect. There we go. Questions? Well, so this function is not defined at those 2 points, but it can be helpful to know what's going on near these points that our function is undefined. So I'm going to start with our most basic rational function, our parent rational function, f of x equals 1 over x. We know that x can't be equal to 0 because that creates the 0 in the denominator, which is a problem. But we want to know, how does our function f of x behave as x approaches 0? When you get into the end of pre-calc and calculus, we'll call this the limit. For now, I'm not going to use the calculus notation, but just know that if you are going that route, once you hear the limit, it's basically the same thing that we're talking about here. So, talk about what happens as x approaches 0. And we could either approach 0 from the left side or the right side. So we have a different notation to indicate whether we mean left side or right side. So for left side, we use a little minus because the negatives are to the left. So as x approaches 0 from the left, we want to talk about what f of x approaches. And f of x is just our y value. So let's just follow our graph. As x approaches 0 from the left side, what's happening to our y values?
Decreasing.
They're decreasing, right? They continue to decrease forever, all the way towards negative infinity. Similarly, I want to look at what happens as x approaches 0 from the right side. What happens to the y values then? So again, I'll just follow my graph and take a look. What's happening to the y values?
Increasing.
They're increasing as well, all the way to positive infinity. Questions at all? Okay. Well, we can also look at what happens as x approaches negative infinity. So I'm going to follow my graph. As we go towards negative infinity, what's happening to our y values?
Decreasing?
They're all right, so it's hard. What do you mean by decreasing? Like getting more negative? Is that what you mean? Or
Yeah. Is it
All right.
constant?
getting more negative, it would be pointing down towards negative infinity. Notice how our graph looks like it's getting closer and closer to the x-axis. Right? So the y values, if we're getting closer and closer to the x-axis, are getting closer and closer to 0. Oh, now we want to ask ourselves, well, is it ever going to switch over into a positive number? Because right now, all of these y values are negative numbers. Is this ever going to, kind of go up and, well, not curve like that, but, go up and go into the positive values? What do you guys think?
No, because x can't equal 0.
That's true that x can't be 0, but I'm asking if I put in an increasingly large negative number for x, which is what it means as x approaches negative infinity. So if I put in negative 100, negative 1,000,000, negative 1,000,000,000, is that number ever going to switch to be positive, like the overall value of the function when we plug it into the function?
No,
Why not?
because it would still just be like an infinitesimally small fraction of 1. So unless you switch it to a negative number, it's never going to get, I don't know, it would never cross over, I don't think.
Okay, so it's not ever going to cross over, but I'm going to give you a little bit better explanation on why. If you look at our function is 1 divided by x. So 1 is a positive number. As x approaches negative infinity, we're plugging in negative number. So if I take a positive number and I divide it by a negative number, it's always going to be negative. So our graph is never going to cross the x-axis and move into positive y value. So x, or f of x, approaches 0, but to indicate that I mean the bottom side of 0, we denote it with a little negative because that's the bottom side. And similarly, we can look at what happens to our y values as x approaches positive infinity. So again, we'll follow our graph. And again, notice that it's getting closer and closer to the x-axis. And for the same kind of reasoning before, it's never going to cross the x-axis. As we're proceeding to the right, we're plugging in only positive x values. So if I take this positive 1 and divide it by a positive x value, I'm always going to have a positive number. So f of x approaches 0 from the positive side. So we've got these two different lines, one on the y-axis that our graph is getting closer and closer and closer to, but not actually touching, and then one here on the x-axis that our graph is getting closer and closer and closer to, but not actually touching. These lines are called asymptotes. We're going to study 3 types of asymptotes in this course. They're all lines: vertical lines, horizontal lines, and then oblique lines, or like diagonal lines, ones that we would get that are y equals 2x plus 3, where you plot the y-intercept and apply the slope. So our vertical ones are always x equals a number, horizontal lines are always y equals a number, and then the diagonal ones is something like y equals mx plus b. In this section, there's quite a bit of setup before we get to put it all together in one problem. All right, let's talk about vertical asymptotes. The line x equals a is a vertical asymptote for the graph of a function if f of x approaches positive or negative infinity as x approaches a from either side. So as our x value approaches a particular number, our y value approaches either positive or negative infinity. And we saw that happen up here. It was the first two here. as x approached 0 from either side, our y value approached either positive or negative infinity. And that tells us that we have this vertical asymptote. Vertical asymptotes can look, kind of some different ways. So I have the vertical asymptote dashed there in the red. An asymptote isn't actually part of the graph. It's more like a guideline for the graph. So typically when we draw them in, we use dashed lines to indicate that we're not including. So I have my vertical asymptote there in the red, and then our first two pictures, we see that our y value is heading towards positive infinity from either the left or the right side. And then the bottom two shows how our graph is approaching negative infinity from either side of our asymptote. Please note that a rational function can have 0, 1, or several vertical asymptotes. I'd say vertical asymptotes are the most common types of asymptotes that we run across with rational functions. And the graph of a function can never, ever, ever cross a vertical asymptote. We're going to learn that the other two types of asymptotes can be crossed. Vertical asymptotes absolutely cannot be crossed. Rational functions also have the possibility of having a hole in their graph. And what I mean by a hole is that their graph was doing its thing, there was a hole, and then it kept going doing its thing as if the hole never happened. A hole happens when there is a common factor in the numerator and denominator of your rational function. Like if you factor the top and the bottom, and then you can cancel a common factor and simplify, then there's going to be a hole at the 0 of that common factor. So we're going to practice locating our vertical asymptotes and holes. We actually start by looking for the holes. We're going to factor the numerator and denominator of our rational function completely. Then we're going to look to see if there is a common factor. If there is a common factor, we're going to cancel it out and simplify our rational function. We're then going to note that there is a hole at the 0 of that common factor. Then we're going to move on to looking for vertical asymptotes. Vertical asymptotes exist at the zeros of the simplified denominator. Now, if the rational function didn't simplify, if there wasn't a hole to begin with, then there is no simplified denominator, so you'll be looking for your vertical asymptotes at just your original denominator. So let's see how this would work. We want to locate any holes or vertical asymptotes. The first thing we want to do is factor our rational function's numerator and denominator. The numerator doesn't factor. I like to put parentheses around it to remind myself that's one whole factor. But our denominator does factor. Factors into 2x plus 5 times x minus 3. Do we have a common factor in the top and the bottom?
No.
No, we don't. So that means that there are no holes. So this one doesn't have a hole. Holes are less common. Next, we want to move on and identify our vertical asymptotes. Our vertical asymptotes are located at the zeros of our simplified denominator. So since our denominator didn't simplify, we're just looking at this denominator right here. Since there are two factors, that means that we're going to have two vertical asymptotes. And I tend to just abbreviate VA so I don't have to write it all out. What are our two vertical asymptotes going to be?
-5/2 and 3.
All right. So you got the right idea. We just need to make a slight change in the notation. You have to write x equals in front of each of the numbers. What we're doing is writing equations of lines. So with a vertical line, you have to have x equals a number. I will not accept even if you do like this, right? Bad notation. You would never write two equations, you know, y equals 2x plus 3 comma negative 5x plus 1, right? We'd write y equals for both of those. So we need to do that same thing here as well. Questions? All right, let's try another one. We're going to start by factoring the numerator and the denominator. We got a GCF in the top, and then our denominator factors as well. Do we have a common factor this time?
Yes.
We do, right? This right here can be canceled out and our function simplifies down to g of x equals x over x minus 3. Now, since we had a common factor, that tells us that we're going to have a whole. And the whole exists at the 0 of that common factor. The factor is x minus 4, so the 0 is x equals 4. And again, you got to have that x equals there. Questions on the whole? So our vertical asymptote, how many are we going to have?
One.
Just one, because we need to be looking at our simplified denominator. And the vertical asymptote is going to exist at the 0 of that simplified denominator. We're going to have a vertical asymptote at x equals 3. A whole at x equals 4 and a vertical asymptote at x equals 3. Questions on identifying wholes or vertical asymptotes before we move on to our next type? All right, next up are horizontal asymptotes. The line y equals b. So this time, since we're doing a horizontal line, it's y equals a number. The line y equals b is a horizontal asymptote of the graph of a function f if f of x approaches b as x approaches either positive or negative infinity. And if we scroll back up to when we looked at 1 over x, our definition says that there's a horizontal asymptote if f of x approaches one particular number as x approaches positive or negative infinity. And that's exactly what we have here. Our y value is approaching this particular number 0 as x approaches positive or negative infinity. And that's how we got that asymptote on the x-axis. So I have a bunch of pictures here on how horizontal asymptotes can look. That our graph could either be tending towards positive infinity or negative infinity as it gets closer and closer to this particular y value. I always think of a horizontal asymptote of like where the graph levels off. It never goes totally horizontal. It's always getting closer and closer and closer to the asymptote, but it's kind of like where we, to use a trendy term right now, it's where the curve flattens. It levels off. You'll notice in my third picture over here that it shows that a horizontal asymptote can be crossed. It just so happens, though, that one of the ends has to come back and tend towards the asymptote. Your line can't just cross it and ignore the asymptote there. One of the ends of the graph has to get closer and closer. All right, so I got some notes here. What do I say? Horizontal asymptotes imply that a function approaches a constant value as x gets large in either the positive or the negative direction. And that's the whole just leveling off that's occurring. And as I mentioned, it can cross a horizontal asymptote, just not at the ends. The end, one of the ends has to get closer and closer to the asymptote. The way that we locate horizontal asymptotes, it's all about comparing the degree of the numerator with the degree of the denominator. If the degree of the numerator is less than the degree of the denominator, then your horizontal asymptote exists at y equals 0, the x-axis. If the degree of the numerator is equal to the degree of the denominator, you're going to have a horizontal asymptote at y equals the ratio of the leading coefficients. So you'll just divide the two leading coefficients. And lastly, if the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. Yes, you need to remember those three things. I'm going to take a few minutes now to try to explain why we come up with those answers, because it's easier to remember stuff if we actually understand where it's coming from. So let's start with what happens when the degree of the numerator is less. So maybe that's a function that looks like x over x squared plus 1. The degree of the numerator is less. I'm just going to make a little xy chart. And we're going to see what happens to the overall value of this function, our y value, as x gets larger. So I'm going to plug in some numbers. If I plug in 1, I get 1/2. If I plug in 10, that's 10 over 101. Plugging in 100, that's 100 over 10,001. And if I plug in 1,000, I get 1,000 over 1,000,001. Taking a look at those y values, what's happening to the overall value of that fraction as our x value gets larger? And we could pop them in our calculator to get a decimal approximation. All right, this one's like 0.5. This one's like holy moly, it's terrible. 0.1. This one's like 0.01. This one's like 0.001. So the overall value of our fraction is getting smaller and smaller, because the denominator is what we're dividing by. If your denominator, what you're dividing by, is substantially larger than your numerator, dividing by a big number makes the value get smaller and smaller and smaller, so small that eventually it's going to be practically 0. So that's what gives us a horizontal asymptote at y equals 0, because we got a little numerator divided by a big denominator, and when we divide by big numbers, it makes the value get smaller and smaller and smaller. Next up is when the two degrees are the same. Maybe 5x squared over 3x squared plus 1. And I'm going to do the same thing here, make a little xy chart. Plugging in 1, I'm going to get 5/4. Plugging in 10, that's 500 over 301. plugging in 100, that's 50,000 over 30,001. And plugging in 1,000, that's going to be 5 million over 3,000,001. Well, as x approaches infinity, 1 isn't really a big deal, right? I have $5 trillion. If I'm like, I lost $1, it's not a big deal. So I'm kind of gonna drop this 1 in the denominator is not such a big deal as we're going to infinity. So if you look, what happens to these fractions when you start simplifying is you end up with the same number over and over again, 5/3. And that 5/3 is the ratio of our leading coefficient. So with this one, it's kind of the thought that your variables are increasing at kind of the same rate because the degrees are the same. So the variables in your numerator and denominator are increasing at the same rate. The only thing that makes a big difference is the multiplier out in front. So when your degrees are the same, your horizontal asymptote is the ratio of your leading coefficients. Any questions, anybody so far? All right, let's look at the last situation when the degree of the numerator is larger than the degree of the denominator. This is just, I'm going to get just the reciprocal of the y values I got for the first one, the red one. So if we take a look at the overall value of these fraction y values, notice that the numbers just keep getting bigger and bigger and bigger. They're never going to level off at a particular number because I've got a big numerator divided by a small denominator. So since we're dividing by a small number, it never levels off the number. It just keeps growing. Therefore, we have no horizontal asymptote. So that's just kind of some explanations of behind the rules to try to help you remember the rules better. If the degree of the numerator is less, horizontal asymptote at y equals 0. If they're the same, y equals the ratio of the leading coefficient. If the degree of the numerator is larger, then there is no horizontal asymptote. So let's identify our asymptotes. This first example, f of x, we have the situation where the degree of the numerator is less than the degree of the denominator. What does that mean for our horizontal asymptote? Are we going to have one?
Yes.
Yes, we are. And where is that horizontal asymptote going to be located?
Y equals 0.
At y equals 0, because I have this little number in the numerator divided by a big number in the denominator. Over time, it's going to get smaller and smaller until it's practically 0. Great. In our next example here, we have that the degree of the numerator is equal to the degree of the denominator. When they're equal, they're growing at about the same rate. The only thing that makes a difference is the multipliers out in front. So we have a horizontal asymptote at y equals the ratio of these leading coefficients, 5/1, which of course will simplify down to just y equals 1. Questions, anybody?
Yeah, I didn't get a chance to see what you wrote for the first one. Oh, okay.
So then here in our third example, we have the degree of the numerator greater than the degree of the denominator. So we have a big number in the top divided by a little number in the bottom. Is this ever going to level off?
No.
Nope. So we have no horizontal asymptote. Questions on horizontal asymptotes before we move on to oblique? So I don't have pictures for the oblique because they could be like a million different ways they looked, so I didn't bother making pictures. So an oblique asymptote is just a diagonal line, and diagonal lines are always of the form y equals mx plus b. So the line y equals mx plus b is an oblique asymptote, or sometimes it's called a slant asymptote, of the graph of a function f if f of x approaches that diagonal line, the y values approach mx plus b as x approaches either positive or negative infinity. A rational function will have an oblique asymptote only when the degree of the numerator is exactly one more than the degree of the denominator. That's how you know an oblique is going to exist. Oh, just like the horizontal asymptotes, an oblique asymptote can be crossed, but it has to come back and one of the ends has to tend towards that asymptote. So we determine that an oblique is going to exist by looking at the degree, and if the degree of the numerator is exactly one more than the degree of the denominator, we know it exists. So how do we go about finding it? Well, we're going to divide. See, like this one here. Notice how the degree of the numerator is exactly one more than the degree of the denominator. So we would be able to perform division. Remember that when you perform division, the degree of the quotient is always the degree of the dividend minus the degree of the divisor. So every single time, we're going to end up with a quotient that's first degree, because we said that for an oblique asymptote to occur, the degree of the numerator has to be exactly one more. So if it's always a difference of one and the degree of the quotient is the difference, we're always going to end up with a quotient that is first degree, aka linear. So it's going to look like this, right? When we divide, we get something like 3x plus 5, and then we have our remainder, something like this. Well, we're actually going to end up dropping the remainder. And the reason for that is we kind of talked about it when we did horizontal asymptotes. When the degree of the denominator is greater, as you go towards infinity, this approaches 0. So eventually this remainder is going to have a value of about 0, so we just drop it. This will be the only time in math I ever tell you to drop something off the face of the earth. So we're dropping the remainder, and then what we have left here is going to be our oblique asymptote. We just got to put a y equals in front. So let's see how we would do that. We want to locate the oblique asymptote. Well, I know an oblique is going to occur because the degree of the numerator is exactly one larger than the degree of the denominator. All right, so I need to divide. Since what I'm dividing by is x minus 2, I can use synthetic division here. Remember, with synthetic division, if you're missing a term value, right, if it skips, make sure you put in your placeholder. And now we're going to divide. The last number is our remainder. We're going to drop that. Our oblique asymptote is right here. Here's our quotient. but we just need to put y equals in front of it. We get an oblique asymptote at y equals x plus 5. Questions on identifying oblique asymptote? All right, well, let's take every single thing that we've talked about today and put it together into one problem and graph these rational functions. So I'm starting with some rational function. The first thing we want to do is simplify the rational function and identify any holes. Now remember, to do that first step, you have to factor the numerator and the denominator. So I don't know, maybe, I don't know if you want to add like step 0. Or put that as like directions to number 1. All right, so we're going to factor the numerator and the denominator, and then we're going to simplify if there is a common factor and identify any holes. Then we're going to find our asymptotes. In each definition, like directions of our asymptote, it always said that there was no common factor. We go back. Right, no common factor, vertical asymptote exists at the simplified denominator. So once you're ready to identify your asymptotes, you're only looking at the simplified version of the rational function. Then we're going to find our x and y intercepts because they're typically pretty easy points to find. And again, we're using the simplified version of our rational function. Then we're going to draw in all the information that we have gotten so far, all of our intercepts, all of our asymptotes. This is not going to be enough information to graph our function. So we're going to have to get extra points. And the only way to do that is to make an XY chart until we get to calculus. When you get to calculus, you a slick way to figure out exactly how high it is. Kind of like with the polynomials, where we kind of just graphed them generally and said we need calculus to get the perfect graph. Same thing's happening here. But we're going to have such little information that we have to plot some additional points. So we're going to make an XY chart, and we want to choose X values, particularly near the asymptote, so we can see how it behaves. Here, when you're creating this XY chart, it's important that you use the original version of the rational function. We're going to plot these additional points, and then we are going to connect all our points, have our ends tend towards the asymptote, and everything should be a nice smooth curve when you draw these in. All right, so we want to graph the function g of x equals 2x squared minus 7x plus 6 over x squared minus 3x minus 4. We'll identify any holes, asymptotes, intercepts. We'll also state the domain in interval notation. Even though domain is the last thing on the list of directions, I would definitely do it first. To find the domain of a rational function, you simply set the denominator equal to 0, solve, and exclude. The reason I like to do the domain first is because the domain you have to use the original version for. And for so much of this, we use the simplified version that I'm afraid that I'm just going to be on autopilot and use the simplified version for the domain. So I like to do the domain first. Factors nicely. So x cannot be equal to -1 or 4. I put this on the number line. I can't have -1 and I can't have 4. All of this stuff. So that makes our domain negative infinity to negative 1, negative 1 to 4, and then 4 to infinity. Questions at all on identifying the domain? Next up, we want to look for holes and asymptotes. To find the hole, we know that that exists at any of the zeros of any common factors. So I need to get this factored. And all of these should factor nice. You're not going to have to do any of that, like listing possible rational zeros and testing. You're not going to have to do any of that kind of stuff in here. These should factor nicely by traditional methods. Our numerator factors into 2x minus 3 times x minus 2. And then our denominator, we actually already did. So I'm just going to go steal the work from over here. And we get this. Do we have a common factor?
No.
No, we don't. So that means no holes. On to our vertical asymptotes. Our vertical asymptote exists at the 0 of our simplified denominator. Our denominator didn't simplify, so we're basically just looking at the original. But I want to look at the factored form because that's how I get the zeros. So looking at the factored form of our denominator, where will our vertical asymptotes be?
X equals 4 and x equals -1.
Perfect, and perfect notation, right? We need that x equals in front of each of those numbers. Great. Next, we're checking for horizontal asymptotes. This is where we compare the degree of the numerator to the degree of the denominator. Personally, I don't like to look at a factored form to do that degree comparison, and we need the ratio of the leading coefficients anyway. So you want to look at the multiplied out version. Had our g of x simplified, I would have like distributed everything that was left to get the multiplied out version, and we'll see that in the next one. All right, so I'm going to look at the original here, though. We have the degree of the numerator being equal to the degree of the denominator. When that happens, our horizontal asymptote is at y equals the ratio of our leading coefficients, which is 2/1. So that means horizontal asymptote at y equals 2. Any questions so far? For an oblique asymptote to occur, the degree of the numerator has to be exactly 1 larger than the degree of the denominator. Is that our case?
No.
No, it's not. So that means that there is no oblique asymptote. It's a fact that an oblique asymptote and a horizontal asymptote can't exist at the same time. An oblique asymptote only occurs when the degree of the numerator is exactly 1 larger than the degree of the denominator. Well, for horizontal asymptotes, if the degree of the numerator is larger, there is no horizontal asymptote. So any of the other combinations can occur. You can have vertical with oblique, vertical with horizontal, but you can never ever have horizontal and oblique together. All right, on to our intercepts. Do x-intercepts first. To find any x-intercept ever in our life, we let y be equal to 0 and solve for x. Make sure that if your function simplified, you're using the simplified version here. And it's up to you. You could either use the factored form or the multiplied out. I think it's about equal here. All right, we want to solve for x. This is a rational equation, but it's a special kind that I like so much called a proportion. And I love a proportion because that means I can cross multiply. 0 times our denominator is just 0. And then 1 times our numerator is our numerator. And we want to solve this quadratic equation. Factoring is always my first choice. And hey, we already factored the numerator over here, so I'm just going to steal this work again. Setting each one of these equal to 0 and solving, we get x to be 3/2 and x to be 2. So that means 2x intercepts 3/2 comma 0 and 2, 0. Questions on finding our x-intercepts? All right, on to our y-intercept. To find any y-intercept ever, we let x be equal to 0 and solve for y. I definitely like the multiplied out version for y-intercept, and I'll show you why here. Each term that contains an x, when I plug the 0 in, each one of these terms just wipe out because they end up being 0, and my y-intercept is the ratio of my constant. So I like to use the multiplied out version. For that reason, it seems easier. This is 6 over -4, which is -3/2. So that gives me a y-intercept of 0, -3/2. We want to plot the points we have, which aren't many, right? We only got 3 points, and draw in our asymptotes. 0, -3/2. 3/2, 0, and 2, 0. And then our asymptotes, we have verticals at x equals -1 and x equals 4. And when I draw this in, you'll see I'm going to use dashed lines. See it a little better. I'm going to use dashed lines because technically it's not part of the graph. It's just like a guideline. And another one at x equals 4. And then we have a horizontal asymptote at y equals 2. Sorry, I can't make my marker skinny when I go this way. All right. But that's all the information we have, which is really not a lot. Like, I know that these 3 points have to connect, and other than that, I don't know anything. Notice that our vertical asymptotes have kind of broken up the plane into 3 regions. We have, this side, and then this side, like in between the 2 asymptotes, and then over here to the right. When creating our XY chart to get additional points, we want to choose X values in each of those 3 regions. So I'm going to start by choosing X values to the left of that first vertical asymptote. I'm going to choose -8 and -4. Then I need to choose, you know what, I'm going to do one more. Let me do -2 as well. Okay. Then I need to choose some X values that fall in between my 2 vertical asymptotes. Since I have some points here, I feel like I guess I know a little bit more about the graph. I know that ends of the graph have to tend towards the asymptote. So this here, I'm super confident is just going to keep going and get towards the asymptote because it's already really close. But the other side, I'm not so sure. It might come down like this, or since horizontal asymptotes can be crossed, it might pop up like this and do something that looks kind of cubic. I'm not sure which one it is. So I'm going to choose the x value of 3 to see what's going on, like right here, whether it continues down or flips up. So x value of 3. And then lastly, I need to choose some numbers to the right of this second vertical asymptote. It's at 4, so I'm going to choose like 5 and 8. And now we have the tedious process of taking these x values and plugging it in to our original function. You're going to have to plug this in your calculator. Make sure when you do that you have the numerator in parentheses and the denominator in parentheses when you type this in. For the sake of time, I already figured out what all the y values are, so we don't have to spend the time here awkwardly over video chat typing these into our calculator. But that's what you'll have to do. So our y values, we get 2.3, 2.8, 4.7, negative 0.8, 3.5, and 2.2. I'm just going to give you a second to get all those written down. All right, so let's plot these points. Negative 8, 2.3. It's like right here. Negative 4, 2.8. And then negative 2, 4.7. And once you get the points in like a region plotted, we can draw in that part. So I know that these 3 points have to connect. And I also know that the ends of my graph have to tend towards the asymptote. So here on the left, this is going to tend towards the asymptote it's already close to. And here on the right, this is going to continue up because that's the asymptote that it's close to. So I've got this little swoop shape. Our next point to plot is 3, negative 0.8. Which is right here. So that means that these connect with this point. So now I'm confident that this is going to be kind of a parabolic shape. And our end is going to tend towards the asymptote that it's closest to. There we go. Any questions so far? All right, our last couple points to plot. We're doing 5, 3.5. And then 8, 2.2. And if you feel like you want more points to plot, then please feel free to choose more x values when making your XY chart. These 2 points connect. The ends have to tend towards the asymptote. So here to the right, this is going to tend towards the horizontal asymptote. And here on the left, this is going to tend towards our vertical asymptote. And there we go. There's the graph of g of x equals 2x squared minus 7x plus 6 over x squared minus 3x minus 4. Questions? Don't worry, the graphs are, I think, all multiple choice on my math lab, so you won't try to have to graph this thing on my math lab. Anybody? Questions before we move on to the next one? Anybody need another minute? All right, let's graph one more. We want to graph the function h of x equals x to the third minus x over x squared minus 2x minus 1. Again, we'll identify the holes, asymptotes, intercepts, and state the domain in interval notation. I always start with domain. This is where we're going to set our denominator equal to 0, solve and exclude. We get that x can't be equal to positive 3 or negative 1. Two numbers to exclude here. Oh, we get a domain. Negative infinity to negative 1. Negative 1 to 3. And then 3 to infinity. Questions on the domain?
Yeah, I have a question quick. With
Yep.
the number line, are you going to want us to draw that on like
No,
a test
no.
or quiz, or is that just something for like a
No,
visual?
that's just, I'm trying to give a visual to
Okay.
people that we're excluding those two numbers and we want the middle. Because frequently, not so much at this level, but especially when people are first learning it, people tend to forget this middle part. So I've always kind of just drawn the number line to give people a visual for that. Anybody else? Okay, next up are our holes and asymptotes. We actually start with holes first, and holes happen if we have a common factor. So I'm going to need to factor this. The numerator here is going to be a two-step process. For factoring, notice it has a GCF, and then after we take the GCF out, we have the difference of two squares. So this factors into x times x plus 1 times x minus 1. And then our denominator is x minus 3 times x plus 1. Do we have a common factor in this example?
Yes.
Sure do. Right, x plus 1. So we're actually going to simplify our function down to x times x minus 1 over x minus 3. And since we had a common factor, that means that we have a hole. And where's that hole going to be located?
X equals -1.
X equals -1. Perfect. And now we're going to run through our asymptotes. First is a vertical asymptote. Remember, for all our asymptotes, we're using the simplified version. So our vertical asymptotes exist at the zeros of our simplified denominator. We're looking over here. We're going to have just one vertical asymptote, and it's going to occur at x equals 3. To identify our horizontal asymptote, this is where we compare the degree of the numerator with the degree of the denominator. As I mentioned before, I like a multiplied out version. So even though this is simplified, I'd take a second and then I would multiply it out. I feel like it's easier for me to compare the degree of the numerator with the degree of the denominator when it's not in factored form, especially if I end up needing the ratio of the leading coefficients. All right, so we have the numerator being degree 2 and the denominator being degree 1. Are we going to have a horizontal asymptote?
No.
No, we're not. We never have a horizontal when the degree of the numerator is more. Now we're moving on to an oblique asymptote. An oblique asymptote only occurs when the degree of the numerator is exactly 1 larger than the degree of the denominator. Is that the case?
Yes.
Sure is. So we will have an oblique asymptote at y equals something. I just got to figure out what that something is. To figure it out, we need to divide x squared minus x by x minus 3. Since our denominator is x minus 3, we should be able to use synthetic division. Did somebody have a question? All right, let's divide. Notice that we're missing our constant term, so I need to be sure to put a placeholder in for that. Six is our remainder, which we are going to drop off the face of the earth. And this right here will be our oblique asymptote. We just need to write it in the right form. Oblique asymptote at y equals 1x plus 2. Of course, we don't need the 1 in front of the x. I'm just trying to show where everything's going. Questions on any of the asymptotes or the whole? All right, intercepts are next. Remember, for our intercepts, we got to use this simplified version. So for any x-intercept ever in our lives, we let y be equal to 0 and solve for x. I'm going to cross multiply. Zero times our denominator is 0. 1 times our numerator is our numerator. And we're going to solve. We get x to be 0 and positive 1. But we know since they are x-intercepts, we need to be sure to write them as ordered pairs. We get 0, 0, and 1, 0. Questions on the x-intercepts? Y-intercept is next. Again, simplified version, we're letting x be equal to 0 and solving for y. I get 0 over negative 3, which is 0. So y-intercept of 0, 0. Please note that anytime you have an x-intercept, you're also automatically going to have, I'm sorry, I didn't say that right. If you have an x-intercept of 0, 0, you automatically have a y-intercept of 0, 0 as well. So if you see that, you really don't even need to do the work. You know your y-intercept's the origin as well. All right, let's get the information we have plotted, and then we will choose some extra points. The only 2 points I have to plot are 0, 0 and 1, 0. Not very much information. Excuse me. And now I have a vertical asymptote at x equals 3. And then an oblique asymptote at y equals x plus 2. The way that you're going to draw this oblique asymptote in is exactly the way you would just graph the line y equals x plus 2. The only difference is that when you get your points, you're not going to do a solid line, you're just going to do a dashed line. So I'm going to start with my y-intercept of 0, 2, and then we apply our slope of 1 over 1. I'm just using my green pen because my marker's so wide. So there we go. Typically, when we have one vertical and one oblique, your graph is either here and here, or it's on the other side. They're always opposite each other, like here and here. But we want to make sure we get a good drawing in, so we're still going to need to get some points, even though I'm super confident that our graph's going to be like here and here. Okay. We only have one vertical asymptote, so we're only looking at 2 regions to the left and to the right of that vertical asymptote. So let's choose some numbers kind of out this way. And then I'm also definitely going to choose positive 2. I don't know, what sounds good. So let's do negative 6, negative 3, and then positive 2. So that takes care of to the left of our vertical asymptote. And then we'll go just on the right. I'm going to do 4, because that's just on the other side of the vertical asymptote. And then 6 and 8. And just like the other one, I already went ahead and found all the y values for the sake of time. So there we go, negative 4.7, negative 2, negative 2, 12, 10, and 11.2. And we'll plot them. I have all my points in this first region, so I'm going to connect my points, knowing that the ends of my graph have to tend towards my asymptotes. So we get this shape right here. And I will do the other side, so 4, 12. 6, 10. And then 8, 11.2. Oh, that looks kind of weird. I feel like I don't know quite where to draw that in. I think I'm going to grab another point. I think I want to know what's going on at 5. So 5 ends up being 10 as well. All right, I just feel a little more comfortable with that because I didn't know quite exactly how it dipped down. All right, now I'm going to connect these points, and I know my ends are going to tend towards my asymptotes. So there we go. so close to being done. There's one more thing we have to take into consideration. We have a hole at x equals -1. Right, hole. So once I get my graph done, I need to come back and draw in the hole. See, it's going to be easier for you to erase and then put in the hole. I'm going to put in the hole, erase, and then come back and draw it back in. A hole does not change the trajectory of the curve at all, which is why I like to do it at the very end. The asymptotes do dictate how the function, goes, but the holes don't. And there we are. That's graphing rational functions. What questions do you guys have? All right, well, that's all I have for today. On Tuesday, we are going to do polynomial and rational inequalities, and we're going to do variation, and then that is going to be the end of Unit 3. So we're going to be having a test a week from Tuesday. I still haven't worked out all the details. I think I'm going to have like a 24 or a 48-hour window where you guys can take the exams. The exams are going to be on My Math Lab. So I will have more details for you on that next week. Anybody? Any questions about anything?
You said what day would the test be?
So it's going to be scheduled for a week from Tuesday, but I'm likely going to do like a 24 or a 48-hour window. So maybe it'll start at 12 a.m. on Monday and then be due at 11:59 p.m. on Tuesday, or it'll start Tuesday at 12 a.m. and then go to Wednesday on 11:59. So I'll let you know for sure next week.
Gotcha.
Anybody else?